Okay, so guys, today gonna learn about the art process of nucleosynthesis. So, when and where does this occur? So, this occurs when there is a collapse of the core of a supernova. So, during the core collapse of a supernova, the process by which nucleosynthesis of newer elements occurs is the R process. So, if this was my star, and this happens in the massive stars, which are almost more than equal to 8 m, where m is the solar mass, the mass of a sun, of our sun. When this star is in its latest stage, then what happens? The fusion that is providing a force in the external or direction from the core and counterbalances the gravity. This is called the thermal pressure, and this is called the gravity. And this thermal pressure is generated by fusion. So what happens in the later stage is that this fusion occurs no more because of no reaction. So now let us see what happens if there is no reaction. If there is no reaction, there will be just G. G means the force under gravity, and this force that was holding it or counterbalancing this gravitational force will no more be present. So what happens? This thing would try to collapse, and while collapsing, they would try to bounce back as well, like this. So shock waves will be generated, and a collapse will occur, and so then this nucleosynthesis will happen, and see how this will happen. So first of all, what happens in the later stage? This star, this star would have uh, heavier nuclei undergoing fusion. So what will happen next? This heavier fusion will result in increase in the binding energy of the nuclei. Now, what would this mean? This means the fusion will slowly produce lesser energy with time. So this is termed in literal terms, should be used as progressive reduction in fusion energy. Now what will happen? This energy will cease to be zero after some time, and the process is first Fe I'm sorry, not Fe. With the decrease in energy, Ni56 will form, and this will make the fusion endothermic. And you all know that means heat is being added, plus 8. And then what will happen? The heat produced due to endothermism uh, will will cause the decay of Ni56, and it would decay into Fe56. And after this, no fusion will occur. So that's how the NiFe core is formed. Now you should remember that if we don't have this force, this fusion, this force would be not there. That is countering the gravity. Now this is absent. This is absent. Now what will happen? Uh, Due to gravity, this thing will bounce back. This thing will collapse. This thing will collapse, and there will be a reaction force acting opposite to this. That will be something that will make these particles that are collapsing to bounce away from each other, and this creates this shock wave front, which is something about 70,000 kilometers per second. And when this core is formed, this will become disintegrated into neutrons plus protons plus electrons, and these protons and electrons will further combine with each other to form more neutrons and neutrinos. Now what happens? The neutron flux, neutron flux increases, and when this happens, the neutrons will start colliding, getting captured. These neutrons will get captured by the pre-existing nucleus that has got Z number of protons and N number of neutrons. And then what will happen? We will have Zp comma n plus 1 n, means one neutron number would increase. This process is a very rapid process, and it won't allow beta minus decay to take place. So then what will happen? This beta minus, the neutron decay will occur as long as there is no stable nucleons produced, and after one is produced, they can stop. But obviously, if the neutron flux is high, neutron capture will occur. The neutron flux decreases, then it has no capability to capture a neutron, right? So then what happens? Beta minus decay will occur. This beta minus decay will occur in a series like the neutron decay was occurring. So to give a good example, I'll start with this C. Then we have this PR, praseodymium, and ND, neodymium. So I'm coming to this diagram and I'll explain this. This is D, right? 3, 4, 5. So C, this is 141, 140, 141, 142. Yeah, you tend to be a bit small, thinner. 41. So now this happened because cerium 140 incorporated a neutron, and it became 141 mass, and after that it became 142 mass. So this was neutron capture, and after that there would be a beta decay from here, so the mass number will be conserved, and here we will have 141 praseodymium, 142 and 143 and 144, and these all can come from this, and this all can come from this as well with neutron decay. Now the same happens for this one, 142, 143, 144, 145, 146. So these are the beta decays. The diagonal ones are the beta decay, and the straight arrows are the neutron decays, neutron captures. So that is how it happens. And after this, we would have Nd and praseodymium converting to a neodymium, and whenever we have transition from one element to the other, we see there is a beta decay, and when it is not there, means it is converting from one element to its isotope, then it is a neutron decay plus neutron capture. And when it's from praseodymium to neodymium with the same atomic number, then it is beta minus decay. And if you are not too much acquainted with what this means, beta decay. So beta decay is something this. So beta decay oh, my pen is not working. Beta decay occurs when a neutron gets disintegrated into a proton and electron with the ejection of an antineutrino particle, antineutrino. Then it's called a beta decay. And if it is neutron capture, then what happens if there is a z number of neutron and n number of proton, z number of protons and n number of neutrons in a nucleus species, and we add a plus n, and then there is zp and n into n plus 1 with the release of gamma energy. So this is called neutron capture. This is a very rapid process, so whenever there is a high, it occurs whenever there is a high neutron flux, about 10 to the power 22 centimeters square per second. So that is when this thing occurs, this thing. And then after that, when the neutron flux, this flask decreases, then the path that is taken is beta decay. So now it should be more clear what happens here. When cerium 140 is having a nice influx of neutrons, it will turn into 141C and subsequently to 142C. And when the influx is low, then it will follow a diagonal path, and it take the beta minus decay path to form the praseodymium, and next this praseodymium will also go on in the neutron capture path. If there is a high neutron influx, then it will move on in this path, and if not, then all this you can see are unstable, so they will follow a beta minus decay path. They follow beta minus decay path, they will form neodymium. So that's how